Hello there, my name is Gregory Carlson. Welcome to 2.7 Part 3. We just talked about how to tell if a function is even, and it's nice that it works out, that it has even exponents typically if it's even. Let's see, a function is symmetrical to the x-axis if it's the same on top and on the bottom. So we just talked about being symmetrical to the y-axis. Let's talk about being symmetrical to the x-axis. And you'll notice that if something is symmetrical to the y-axis, like for example this, would be symmetrical to the y-axis or to the x-axis because it's the same on top and bottom, that it can't be a function. So it's not going to be a function because it won't pass the vertical line test if it's the same on the top and the bottom. You'll also notice that in these graphs we're doing stuff to the y, like it's y to the third or y squared. So if you see kind of stuff happening to the y, then that's a clue that it maybe isn't a function. The way you tell if it's symmetrical is you do the same thing that we did last time, where we plugged in negative x for x, except this time we plug in negative y for y. So every time you see a y, you replace it with negative y, and simplify it to see if you get the same equation. So this negative y, when it gets squared, will turn into positive y squared. So you see that we are symmetrical to the x-axis. And that doesn't have a special name because truthfully we don't look at this very much because it's not a function. So that's symmetrical to x-axis. How about this one? If we plug in a negative y here, you can probably guess what's going to happen. Because we have negative y to the third, that negative doesn't cancel. And so these two equations are not the same, so that's not symmetrical to the x-axis. Do you think that it would be symmetrical to the y-axis, though? Yes, because of that x to the 4, if we replaced x with negative x, we would get the same equation. So this one would be symmetrical to the y-axis, but as we can see, not the x-axis. This one's kind of the opposite. If we plug in a negative y for y, we get this. The negative cancels because of the square, so that is symmetrical. It is symmetrical to the x-axis, but it would not be symmetrical to the y-axis, because if we plugged in a negative x here, we'd still have the negative, so it's not symmetrical to the y-axis. Lastly, let's do this one. Let's plug in negative y for y, and we could take off both of these negatives and make it y equals 2x, which is different than y equals negative 2x. So this graph is not symmetrical to the x-axis. So that's a good skill to have. So the way you tell if something is symmetrical to the y-axis is you plug in a negative x for x. That has a special name. If a function does that, it's called even. Otherwise, if we want to see if it's symmetrical to the x-axis, meaning the same on the top and the bottom, you replace negative y for y and see if it works out to be the same. This one's not as common. How do we tell if something is symmetrical to the origin? Something is symmetrical to the origin if it's symmetrical to both the x-axis and to the y-axis. So basically what we do is we do both. We replace x with negative x and y with negative y, and we see if it's going to be the same equation. So this equation would be negative x. The negative on the y would cancel. So we see that this is not going to be symmetrical to the origin. So that's not symmetrical. What about this one, though? X squared plus 2y squared is 9. If we plug in a negative for both of them, 2 times negative y squared, you can see that on this one, both the x and the y are going to cancel and become positive. And so this matches this. So we plugged in both of them, so that's going to be symmetrical to the origin. Okay, how about this last one? X squared plus y squared, 2x to the 4, y to the 4. Hopefully you can see that if we plugged a negative into each one of these, all the negatives would cancel. Because all of the exponents are even. And this would just turn straight back into this because all of the negatives would cancel. So that would be symmetrical to the origin. Okay, so we've seen symmetry to the y-axis, symmetry to the x-axis, symmetry to the origin, which is a combination of these two. The last thing I want to show you in this part is we've looked at when a function is even. So when is a function odd? And a function is odd if this happens. When we plug in a negative value for x, it should turn the y value negative. So that's kind of hard to explain, so let me show you it visually. This would be an example of an odd function. You see, let's say I plug in 3 for x and I get this value. When I plug in negative 3 for x, I get the same value except it's a negative value. So it's kind of like if you go to the right and up, if you go to the left the same number of spaces, you should go down the same number of spaces. Here's another example of something that's odd. You can see that this graph going into the first quadrant is the same going into the third quadrant. Or if we go positive 2 up 8, you get the same point going negative 2, negative 8. That's symmetrical. So it's kind of if the first quadrant is kind of symmetrical to the third quadrant, or if you had, that's how you know it's going to be an odd function. Here's another odd function. You see that it kind of reflects a little bit. It's not the same as reflecting across the origin, but you see that if we go over and up, we can go over and down. So that's what it looks like on a graph. Here's how to tell in an equation. We plug in a negative value for x, and we need to see if the whole function turns negative. So here you can see I've got the function. I'm going to replace the y with x, f of x, if that's okay. So I have f of x equals 2x to the third. Let's plug in negative x. So I'm going to replace every x with a negative x. Do you see that? And this negative is going to survive the odd power and come outside like that. Do you see that? And now look, we have 2x to the 3. But what is 2x to the 3? F of x. 2x to the 3 is f of x, so I can replace that with f of x. And that satisfies the definition of being odd. If we plugged in a negative x, it turned the entire function negative. When I plugged in a negative x, it turned the entire function negative. So that means it's going to be symmetrical in the first and third quadrant like I showed you. So this is an odd function. Is this an odd function? Let's plug in negative x. And we see that that's not going to be this entire thing being negative. This, in order for this to be odd, this would have to be negative, and this would have to be negative. We'd have to be able to pull a negative sign out, and we can't do that, so this is not odd. That doesn't make it even, it's just not odd. How about this one, though? Is this one odd? Again, I'm going to replace it with f of x. Let's plug in the negative x now. See how I did that? That negative sign is going to come out in front. And we know what 5x is. 5x is equal to f of x. So we get f of negative x is equal to negative f of x. And so that means this is odd. So that's what we want. We want f of negative x to equal negative f of x. Remember, it's negative f of x being the 5x. Let's do this last one. Let's replace it with f of x. Just replace y, I mean. Okay, let's plug in negative x. Inside the parentheses. So there you go. The negative is going to survive both of these odd exponents. Again, notice that if something's odd, chances are we're going to have odd exponents. So it's nice that it works that way. So the negative sign will survive. So we get f of negative x is equal to negative x to the 3 minus 4x to the 5. And do you notice how this time I have a negative in front of both of them? This one failed because I didn't have a negative in front of both of them. But this one does have a negative in front. So look what I can do. I can factor out that negative, which will change both of the signs. And then if I do that, what do I have in the parentheses? Look, it's f of x. It's x to the 3 plus 4x to the 5. And so I can replace all of that with negative x. With negative f of x. So we got f of negative x equals negative f of x, so this is an odd function. So sorry this is taking so long. The most important ones are telling if something is even or odd. You also know how to tell if something is symmetrical to the origin. So just make sure you can do all of these: y-axis, x-axis, origin, and tell if something is odd. They're all a little different. So if you need any help, just review the video, and I'll see you in part 4. We have one more problem to go.